that is glass and plastics, on soil physical functioning. So for those of you who were at the Canberra conference a couple of years ago, I gave a similar presentation on, I guess, the first stage of this work, which was to look at some experimental plots that the New South Wales DPI had set up back in 2014, looking at the effects of various soil amendments on subsequent wheat yield, as well as some soil properties. And so some of these amendments contained physical contaminant particles, that is glass and plastic fragments. And the two main treatments that we were looking at for this piece of work were the mixed waste organic output treatments and also the garden waste compost treatments. And so both of these treatments were applied at rates of 20, 60, 100 and 200 tonnes per hectare, so small plots. The DPI's Centre for Recycled Organics in Agriculture near Camden, and they had two blocks of different treatments, and on the side of Navigation Creek, which runs into the Nepean River nearby. And we were looking at the 8 MWU and GW plots on both sides of that creek in blocks 1 and 2. And so what I was reporting on back in the 2018 conference was just how much is there of physical contamination in these treated soils. So we're looking with, in this case, another honours student. I was looking at by mass how much glass and film plastic, flexible plastic, and how much rigid plastic was there in these treated soils, and where in the profile were they. Obviously, most of the soil would have, most of the material would have been incorporated to the depth of ploughing, which would have been around about 15 centimetres. But we looked at just how much there was by mass at 2 centimetre increments down that profile to about 20 centimetres. And so what we found was that even though the percentages by mass of the total soil mass were very, very small for rigid plastic, film plastic and glass, because of the lightness of these materials, the number of individual particles was still quite substantial, as you can see from these images here. So these images down the bottom here show individual particles from a handful of soil, basically. And so even though we're only talking about 0.6% rigid plastics, 0.3% film plastics, it's still many, many pieces of plastic in a relatively small volume of soil. And so we demonstrated that the plastics and the glass, they don't move very much. They were still sitting in the zone of incorporation, if you like. But there was plenty of individual particles there, despite the fact that the overall mass wasn't great. And so one of the other aspects of the talk I gave 2 years ago was we also did some thin section work on those soils. And you can see from these examples that even though the mass of these particles wasn't huge as a proportion of the total soil mass, you can see on a surface area basis they were everywhere. And so you can see there's lots of organic matter here because these materials were partially composted, so there's plenty of organic matter added to the soil, of course, as part of the treatment. But you can see that enmeshing the organic matter, or in between the organic matter and the soil solids, in some cases blocking the pores, were lots and lots of film plastics that had a very sort of rugose, crumpled up sort of appearance to them, plus the more solid rigid plastic particles, and then occasional little shards of glass as well. And so you can see there's some pretty, from a soil science viewpoint at least, some pretty horrendous scenes here of just a whole mass of little tiny particles of physical contamination in the pores of these amended soils, as well as having some encapsulation of organic matter, encapsulation of soil solids. So yeah, that was a pretty scary sight, I thought, a couple of years ago. But of course, one of the conclusions from that work was, well, it looks pretty horrible, but what actual effect is that physical contamination having on the functioning of the soil? Now, since then, the New South Wales EPA has banned the use of these MWU products being applied to agricultural land, but there's still plenty of land out there that would have this material in it and on it. And so I guess we're interested in seeing, well, what is the effect of these physical contaminants on the possible functioning of the soil? So we returned, Sarah and I, we returned to the same site 5 years after the first study and 6 years after the amendments were first applied to measure on the same plots bulk density, surface penetration resistance as a measure of soil strength, aggregate stability, and surface water infiltration using these fairly common methods: cores for bulk density, cone penetrometer for strength, the ASWAT test for stability, and the Ponder disc permeameter for infiltration rate. And we also had Sarah do a follow-up of estimating the physical contaminant mass in the soil at the two depths of 0 to 10 and 10 to 20 centimetres. So I'm not going to show you this data for the contaminant masses, but I will show you one image that I got Sarah to put together. So what we did was after the bulk densities were measured on the cores of soil, I got Sarah to completely disaggregate those bulk density cores and to pluck out all of the physical contaminant particles. And so what you can see on the right here is the all of the physical contaminant particles extracted from the MWU 200 tonnes per hectare plot in one of the blocks from the 4 bulk density cores. So all of this physical contamination came from 4 of these cores. And so when we first looked at the bulk density cores as they came out of the field, we were a bit worried that we were in the wrong spot because we couldn't see much in the way of visible physical contaminant particles. But when you wash away and disaggregate all of the clay and silt and organic matter, yes, the physical contamination reveals itself. And so, even though it looks pretty benign over here, that's a pretty confronting image of physical contamination coming out of 4 bulk density cores, albeit at the highest rate of MWU application. So it was pretty clear that the plastic and glass hadn't gone anywhere in the preceding 5 years. It was still sitting, where it was placed 6 years ago. So what effect has it had on the physical condition of the soil? Well, the first attribute, bulk density. When you look at these data, you can see that there's a pretty obvious trend where in both the depths of 0 to 10 and 10 to 20, the greatest effect is shown by the highest MWU application rate, 200 tonnes per hectare, and in fact it shows it to be quite significantly lower than the other MWU application rates, as well as in most cases the garden waste application rates as well. So in the fairly limited literature that deals with the effects of physical contaminants on soil, there's a sort of mixed response. Some papers indicate that bulk density is increased by physical contaminant particles. Others suggest that it's decreased. And our information tends to suggest that at the very highest rates of MWU application, you do get a drop in bulk density, presumably because the plastics are relatively light, they're not very dense. And so if you have lots of those particles in there, that's going to combine to make the soil a little less dense overall. So to me, that makes reasonable sense. But again, it was only evident when we got to the very highest rates of MWU application. On to our next attribute, soil strength. You might think that if you've got lessening bulk density, you might get lessening soil strength as well. But we found, even though the data was a bit sort of up and down, we found something of the reverse, really, that generally speaking, as you increase the MWU application rate, the mixed waste, organic output waste, the penetration resistance actually tends to increase with that increasing amount of MWU. And so, obviously, the 100 bomb is a bit of a dip here, but trying to work out why this is the case. Perhaps it's because the rigid plastics and the glass in particular, they're not going to bend or yield to a cone penetrometer tip particularly easily, or as easily as, let's say, organic matter would, or even weakly aggregated soil mineral material. So I'm guessing that even though those rigid plastics and glass, or especially rigid plastic, is quite light, it's going to offer a little more resistance to a cone penetrometer tip than would organic matter or film plastic or organic matter. So I think I can see why there would be a case for having lower bulk density but slightly higher penetration resistance when you have lots of rigid plastics in particular in that soil. What else can I say about this? Generally speaking, the MWU tended to give slightly higher penetration resistances than the green waste applications of the same amount, which I think is for the same reason I've just been outlining, that the rigid plastics offer a bit more resistance than do organic compounds, let's say. On to aggregate stability in water. Where a 0 score is completely stable and 16 is fully dispersed. You can see that we've got some zeros here, so there was very little in the way of dispersion, which I guess is not surprising really, because we're talking about physical contaminants, and so you wouldn't expect those to necessarily change or alter the soil's propensity to disperse. You might expect them to change in their slaking behaviour, but all samples slaked equally, so really there was negligible effect of these treatments on the aggregate stability of that soil. So nothing to see here, basically. On to the infiltration rate. Our initial intention was to measure the hydraulic conductivity using a ponded disc permeameter, but the infiltration was so rapid across all treatment sites that in the end we had to settle for some sort of steady state infiltration rate in millimetres per minute. But even then, there was no particular trend. The sites were all quite overgrown with volunteer pasture species. And you can see here from the image that there's plenty of organic matter there, plenty of little biopores that will be evident there, plus a few shrinkage cracks. And so as a consequence, the water just raced through virtually all of the ponds we set up. And so, there was really no significant effect of treatment that we could see on the water infiltration rate. So to finish up then, what are the overall effects on soil physical functioning of these physical contaminant particles, these glass and plastic particles? As I was saying a little earlier, there's only a limited literature out there looking at the effects of these physical contaminants on physical properties of soil. Some sort of argue that the soil physical conditions are better. Others argue that it's worse off because of these contaminant particles. Here, well, I think the highest MWU application rates have caused the bulk density to come down due to the lighter plastics. That's probably not a bad thing. But also, I think that the highest rates of MWU and therefore the highest amounts of physical contamination have also probably increased the penetration resistance or strength slightly of the soil, and so that's probably not a great thing. But neither of those changes were overly drastic. There was no particular effect on aggregate stability of these contaminant particles. There was no effect on water percolation in this silty clay-loam topsoil. And there was also no visible effect on the volunteer plant growth. It was all pretty lush grass and other weed species across these plots that have been left fallow for about 5 years. So really, to summarise, the overall effect on soil physical functioning is, on at least at this location, not much. So to finish up, I'd like to acknowledge the New South Wales DPI for giving us access to the Crower experimental site to go back to the scene of the crime from 5 years ago, where we did our initial study on these trial sites. And yes, I'm not going to be with you today. Other meetings I've unfortunately have to attend to. So yes, I won't be able to answer any questions online now. But if you want to shoot me an email, I'm happy to talk about things later on. So with that.
The next presentation we have is Mike McLaughlin from the University of Adelaide. Can we have the timer, please?
Oh, you can leave the timer. It's fine.
Presentation.
Okay, so I want to talk about PFAS in soils, for those who don't know what PFAS are. It's a very large group of substances which are in the environment now because of our use of these sort of surfactants for Scotch Guard, Teflon, firefighting, these sorts of things. Rai Kukana should really have been here to present this talk, but he apologises, and I'm speaking in his place, really. So basically, I'll talk a little bit about absorption of what PFAS are, very briefly, and then absorption of PFAS in saturated soils, and then absorption of PFAS in unsaturated soils. So what do they look like? Basically, it's a polyfluorinated substance is where not all the carbon atoms have got fluorine on them. And perfluorinated is when they're all basically got fluorine atoms attached to the carbons. So you've got a tail here, which has got all the fluorine atoms on it, and that's very hydrophobic. And you've got a head group here, which is hydrophilic, it's got a charge on it. The length of this tail can vary from 3 up to maybe 12 or 13 or 14 carbon atoms, so that obviously changes molecular weight. And the head group can change. It can be sulfonamide, it can be a carboxylic acid. You can have amine groups involved as well. So they're quite unusual substances in that they're both hydrophobic. They're called amphiphilic because they're both hydrophobic and hydrophilic. And they've got fantastic properties for forming films and fires. A key point for soils is they've got quite a low pKa, so the acid dissociation constant is quite low. So in most soils, the main forms that we see are anionic, although there are some zwitterionic forms and cationic. Most of them are anionic in soils. The other thing about the carbon-fluorine bond is really persistent. It's the strongest bond in nature, very hard to break. Microorganisms find it very difficult to degrade these substances, so they're very persistent in the environment, very mobile. They're great for firefighting because they form a film on the surface of a fuel fire, and they cut off the oxygen supply for the fire. So they've been widely used at defence sites, airports, all metropolitan fire authorities, country fire authorities. They've all got PFAS contamination. When we're traditionally looking at organic chemicals in soil, we normally look at sorption coefficients and relate it to the organic carbon content of the soil. And we assess the potential hazard of a substance in terms of bioaccumulation based on its partitioning between octanol and water. So for those who've done ecotoxicology, the octanol water partition coefficient is a key property used to judge the potential hazard of a substance. We can't use it with these because these things partition to both water and octanol. So we can't actually use this to assess the potential hazard. And that means that in soils, we can't actually modify the partition coefficient based on organic carbon. Again, for those who know how we look at pesticides, polyaromatic hydrocarbons in soil, we normally divide the partition coefficient, which is the concentration on the soil phase, divided by the solution phase, by the fraction of organic carbon in the soil. It's called the KOC, and again, we use that to look at the potential mobility of pesticides and pharmaceuticals and these sorts of things in the environment. The accuracy with which you measure the partition coefficient is really important because if you do fate studies, just go back. Here you can see, based on 2 different log KOC values, this is how the soil concentration would change over time due to leaching from the soil. So for this particular value here, the lower value, log KOC of 3, most of the contaminant would be removed from the soil in 50 years. For the KOC of 4.2, it would take hundreds of years to remove the contaminant from soil. So it gives you a measure of persistence in the environment. That's why it's quite an important property. Rai actually did a very large literature search. Now these chemicals, they're not new. They were developed in the 1950s. But the understanding of their potential toxicity and mobility in soils is really only in the last 10 years. So it's not like heavy metals that we've known about for hundreds of years almost. Most of the information you'll see in the literature is in the last 10 to 15 years on these chemicals. He did a literature search looking at the KD of PFOS, which is the most common PFAS in the environment, and related it to the organic carbon content in the soils, that partition coefficient. And you can see there's no relationship between organic carbon in soils and the partition coefficient. So we can't really use that KOC, fractional partition coefficient, to look at mobility in soil. We therefore thought, before I go on to that, So in soil there's going to be, Rose mentioned this yesterday, there's going to be various binding mechanisms because they're amphiphilic. So you're going to have hydrophobic mechanisms with organic matter, where the lipophilic tail sorbs to the organic matter in soils. and the hydrophilic head will either sorb to positively charged sites on minerals or organic matter in the soil. And that will depend then on cation bridges, iron, calcium cation bridges, these sorts of things. Because there's so many processes involved in the retention of these, we thought mid-infrared spectroscopy is a really good way to get a very quick snapshot of major soil properties. So it measures organic carbon, not just the content, but the type. It measures not just clay content, but the type of clay. And it's very useful. Within 60 seconds, you get a scan of the soil and you can correlate various properties to that spectra. So we used diffuse reflectance, infrared spectroscopy, and correlated that with KD across 100 Australian soils. This was Emma Knight's work. We took 100 soils out of CSIRO's archive. They varied widely in properties, so going from virtually no organic carbon to 9, very acidic to very alkaline, clay content from 0 to 70%, so a very wide range of soils. We measured the KD of 3 different compounds in those soils and related it to the soil properties. And here you can see the KD value against organic carbon. A little bit of a correlation. We had 100 samples, so it's actually significant, but really it's not very useful. Nothing against clay content and really weak against pH as well. But when we actually used the spectra, we got a reasonable relationship between our measured and predicted KD just using the infrared spectra. So it was a fairly good predictor of the mobility in the soil. And it meant then that we could use mid-infrared to look at heterogeneity across sites, to look at the potential hotspots for PFAS movement, and also across the continent you could do it because we do have a national archive now that's been scanned by mid-infrared. And the main properties that came out of the spectra were not just organic carbon, it was a strong predictor of the KD, but also pH and silt plus clay. So we can't just use that organic carbon normalization. This work I put in because we're in North Queensland, and we actually, because of that relationship with pH, it means that in tropical soils, perhaps with the variable charge in these soils when they become acidic, so in the subsoil, you've got net positive charge in the soil, that could attract the hydrophilic end of the anion, the PFAS anion. So this was work with Paul Nelson and people here at JCU, where we looked at tropical soils. We measured the net surface charge of the soil at various pHs. Danny Oliver did this work, and you can see as the pH drops, the net surface charge will go from negative to much less negative, so there's some positive charges on the edges of the clay minerals or the oxides, and the KD also increased for PFOS in line with that net increase in the net decrease in negative charge, increase in positive charge. So in an individual soil, if you change pH, you will change the partitioning of these. It also means that in tropical soils, these will get held up in the subsoil, where you've got acidic subsoils that have got net positive charge. These compounds will get held up in that subsoil. Rose presented this work yesterday, but very briefly. The conclusions from her work, she looked at a very wide range of PFAS molecules, both the sulfonic acids, the carboxylic acids, different chain lengths, and also some of the compounds that are replacing these. So these compounds are on the Stockholm Convention, some of them. PFOA is going on it, they've been banned internationally. And so Adona and these ones are the ones that are Gen X, are the replacements for these compounds. They're still fluorinated. They're not on the Stockholm Convention list yet. So we looked at those as well to see what their mobility was in relation to PFOS. And the big conclusion from Rose's work, the structure of the molecule really determines the mobility more than the soil conditions. So this is the variation of KD across 10 soils, but plotted against carbon chain length. And you can see as the carbon chain length increased, i.e. as molecular weight increased, it became much more strongly retained in the soil. So longer chain compounds, therefore, are going to persist in the soil for a greater time than these short chain compounds. The final complication with PFAS now is that in the last few years, because they are surface active molecules, they've got that amphiphilic property, they're going to sit at interfaces. And there's lots of air-water interfaces in the soil. And at these air-water interfaces, so it's not sorbing to the solid organic matter or clay in the soil, it's going to be sitting in these menisci, basically in the pores. And this air-water interfacial behaviour could be a potential mechanism for retention in soil as well. And Mark Brusso quite recently published a paper where he did column experiments. This is non-reactive tracer, which is miscible displacement experiments. It comes through with the pore volume effectively. And the PFOS is retarded, but when you look at the binding due to the air-water interface under unsaturated, this is saturated conditions, this is unsaturated, there's much more tailing as it comes through the column. It's being retained in the column at these air-water interfaces. So this is the current thing that we're looking at, trying to work out how important is this behaviour in terms of PFAS retention. It's going to be quite important in soils, clay soils where you've got lots of pores with water held at quite high matrix suctions, and therefore lots of these little air-water interfaces in the soil. Just to summarise, therefore, these chemicals, they're not your typical organic chemicals in soil. They do not behave as hydrophobic chemicals. They've got amphiphilic behaviour. Therefore, you can't use organic carbon to normalise their retention in soil. There's multiple processes in soil controlling their movement and uptake in terms of biota. Infrared looks a pretty good way to estimate both mineral and organic matter components in soil to predict that behaviour. And this unsaturated zone is one that we need to work on now to try and work out how important that will be in terms of their retention in soil. Remember, they're not degraded in soil, they're the forever chemicals. Just like to thank the people who did much of this work. Emma, who's now in Queensland with Jochen Muller, and Rose, who's here at the conference, gave her presentation yesterday. And then Davina, Danny, and people in CSIRO, local collaborators with the soils here, Paul and Ryan, and Les Janik, who's the guru in mid-infrared. And, of course, the funders. Thank you very much.
Any questions? Okay. One question?
So the correlation with infrared, do you think that might pick up the air-water interface through some sort of foresight thing, etc.?
So the question for online people is, would the mid-infrared pick up the air-water interface? It may, but remember, we do the calibration in saturated conditions in the lab, so we're not actually mimicking that behaviour. We'd have to do an unsaturated KD and then try and correlate it to the spectra to see if it did change the calibration.
Okay, I'd like to invite Craig Thornton from Department of Natural Resources and Mines and Energy to come up and talk. Thank you.
Good morning, everyone. I'm Craig Thornton. It's my pleasure to talk to you today about the Brugela Catchment Study, Land Clearing and Soil Fertility. I'd acknowledge my co-author Amanda Elledge, who's with us today, and the Queensland Government for funding the study. The Briglow Catchment Study is located in the Briglow Belt bioregion of Australia. So the bioregion shown in light grey is an area of 37 million hectares, or about twice the land area of Victoria. The bioregion has been heavily impacted by land clearing, with more than 50% of its native vegetation removed. In 1964, the Land Development Fitzroy Basin Scheme, the area shown in dark grey, commenced. This scheme involved government-sponsored clearing of 4.5 million hectares of land for agriculture, primarily as a closer settlement, employment and economic development activity post-World War II. This is a land area equal to about 2/3 of Tasmania. In 1965, the Briglow Catchment Study commenced to determine the impact of this land use change on hydrology and on soil fertility. The study site is indicated by the red star, while the photo shows the native Briglow vegetation in its virgin condition. The study is a paired calibrated catchment design consisting of 3 catchments of 12 to 17 hectares with predominantly clay soils, black and grey vertisols, all with native vegetation of virgin Briglow scrub. The study receives summer dominant rainfall of approximately 700 millimetres per year. Stage 1 of the study commenced in 1965 with all catchments instrumented to monitor rainfall and runoff, and here we can see a flume being installed to collect runoff data. The catchments were monitored in their virgin state for 17 years. Permanent monitoring sites were established in each catchment during this stage, and baseline measurements of soil fertility were undertaken in 1981. Stage 2 of the study commenced in 1982 with 2 of the 3 catchments cleared. Scrub was pulled with 2 bulldozers joined with cable and chain, which was the traditional method of clearing at the time. This method of clearing and the scale with it was conducted within Queensland is no longer allowable due to the modern understanding of the environmental harm that it does. After pulling, the timber was burnt in situ, as these photos show. And here you can see the resultant ash bed across catchments 2 and 3 after burning. After burning, catchment 2 was developed for cropping with the construction of contour banks and grassed waterways. And catchment 3 was developed for grazing with the sowing of buffel grass and improved pasture species. Stage 3 of the study commenced in catchment 2 in 1984 with the planting of grain sorghum, and grazing commenced in catchment 3 in 1983, typically with Brahman and Brahman cross cattle. No fertilisers or feed supplements were used across any catchment at any time. So this is the Briglow catchment study as it looks today. The Briglow scrub control catchment sits within a remnant of Briglow scrub. Adjacent to it, the catchment developed for cropping and the catchment developed for grazing. So what are the impacts of land use change on soil fertility? Well, a key finding is that there are significantly different nutrient dynamics depending on land use. So in the following figures, the Brugela catchment is always shown in black, cropping catchment in red, and the pasture catchment in blue. Focusing on soil organic carbon, the black line shows soil organic carbon in the Brugela catchment, which has essentially remained unchanged over time. The red line shows that organic carbon in the cropping catchment has halved, while the blue line shows that organic carbon in the pasture catchment has generally remained unchanged. However, only 60% of the organic carbon under pasture is derived from the original Briglow vegetation, with the remainder derived from the replacement buffel grass vegetation. So this suggests that a poorly managed buffel grass pasture, potentially through overgrazing, would actually result in a long-term decline in soil organic carbon. Focusing on soil carbon fractions, this figure shows that under cropping, both mineral-associated and particulate organic carbon fractions have declined, but perhaps most interestingly, it also shows a significant decline in what's typically termed resistant organic carbon. In contrast, there was no significant change in any soil carbon fraction over time under pasture. Focusing on soil nitrogen, the black line shows total nitrogen under the Brugela catchment, which has remained unchanged. The red line shows that total nitrogen in the cropping catchment has more than halved, but with the planting of leguminous crops and extreme rainfall, the decline trend may be reversing as shown by the last data point. The blue line shows that total nitrogen in the pasture catchment has nearly halved, and in the absence of a legume, continues to decline. On a kilogram per hectare basis, nitrogen removed from the cropping catchment in grain accounted for 80% of total nitrogen decline. Nitrogen removed from the pasture catchment in beef accounted for 32% of nitrogen decline, while nitrogen volatilisation from urine and faeces accounted for 49% of nitrogen decline. However, nitrogen immobilised in both above and below ground pasture biomass exceeds both of those amounts. Focusing on soil mineral nitrogen, immediately post-burning, ammonium nitrogen increased by a factor of 9, but declined back to pre-burning concentrations within 12 months. Nitrate nitrogen also spiked post-burning, increasing by a factor of 7.5. Elevated nitrate nitrogen was observed under cropping for at least 8 years post-burning, but only 2 years under pasture. The ammonium nitrogen spike was attributed to release from organic matter, followed by subsequent nitrification to produce the nitrate nitrogen spike. Elevated nitrate nitrogen under cropping was likely due to mineralisation, particularly associated with traditional tillage and annual cropping practices, traditional in the early part of the study, and the rapid decline in mineral nitrogen under pasture was attributed to highly efficient uptake and immobilisation by the newly planted buffel grass pasture. Focusing on soil phosphorus, the black line shows total phosphorus in the Briglow catchment, which appears to have increased during the second half of the monitoring period. This is likely due to vegetation-induced nutrient cycling in response to rainfall and movement of phosphorus from further down the soil profile. Total phosphorus increased by 4% in catchments 2 and 3 immediately post-burning, as a result of nutrient release from plant material and deposition in ash. The red line shows total phosphorus in the cropping catchment decreased by 29% post-burning, and the blue line shows total phosphorus in the pasture catchment decreased by 14%. Removal of phosphorus in grain was equivalent to 95% of total phosphorus decline under cropping. And removal of phosphorus in beef accounted for only 2% of total phosphorus decline. Focusing on soil available phosphorus, black line shows bicarbonate extractable soil phosphorus in the Briglow catchment, again generally unchanged. Red and blue lines show substantial increases in available soil phosphorus in the agricultural catchments immediately post-burning as a result of ash deposition. From that point, available P in both catchments declines to pre-clearing or less than pre-clearing levels. Acid extractable P, again, shows exactly the same trend. However, acid extractable P declines to less than pre-clearing concentrations in both land uses. Phosphorus removal in grain was better correlated with total phosphorus than with either measure of available phosphorus, which suggests removal in grain combined with cycling of phosphorus into other pools probably accounts for more of the decline. Phosphorus removal in beef, however, explained 95% of the decline in acid extractable P and 75% of the decline in bicarbonate extractable P. Focusing on soil potassium. Again, black line, total potassium in the Brugela catchment, relatively unchanged. In the agricultural catchments, 5% increase post-burning in catchments 2 and 3, and both catchments have declined very similarly over time, down to about 95% of pre-clearing concentrations. Removal in grain accounts for 39% of total decline, removal in beef, less than 1% of total decline. So that suggests that removal in agricultural products is not the key mechanism of decline in total potassium. Looking at exchangeable potassium, we actually see quite a substantial fluctuation in exchangeable potassium in the Brugela catchment over time, again likely due to vegetation-induced nutrient cycling within the soil profile. There's a loose association between a moving average of rainfall out to about 5 years, above average rainfall periods generally associated with lower exchangeable potassium, below average rainfall periods generally associated with higher exchangeable potassium. Exchangeable potassium increased by a factor of 1.7 post-burning, then over time declining to 65% of pre-clearing concentrations under cropping, 75% of pre-clearing concentrations under pasture. So what do we do with all this information? Scientists, policymakers, landholders, why are we still interested in the effects of land development in the Briglow belt and in particular the Fitzroy Basin? Well, firstly, this is the Northern Grain Zone. This is the most productive broadacre farming land in Australia. Peak Downs in central Queensland, the Darling Downs in southern Queensland, the Liverpool Plains of northern New South Wales. And secondly, because the Fitzroy Basin alone is home to more than 2.6 million cattle. This is the largest cattle herd in any natural resource management region in Australia. It's 25% of the Queensland state herd and it's 11% of the national herd. And thirdly, because achieving these productivity levels has come at a substantial environmental cost. When the Vegetation Management Act 1993 was introduced, 93% of acacia harper filler woodlands had been cleared. And this includes extensive tracts of the Fitzroy Basin, which is Queensland's largest coastal catchment. And it happens to drain directly into the Great Barrier Reef. And as reef health continues to decline, and we have increased focus on the impacts of land use change, we continue to revisit this question of what are the impacts of land use change. So in conclusion, I believe that this 57-year longitudinal study clearly shows the impact of land use change on soil fertility. The long-term data records can be considered a model in their own right and are capable of answering questions well beyond the initial scope of the study. Given the level of foresight and investment that's required to implement and maintain these experiments, it's unlikely that new studies of this nature will be commissioned. So revisiting these historical data sets, applying new analytical techniques to our archive soil samples and adapting the design of the ongoing experiment will allow researchers to answer questions not thought of or clearly not of concern when this study commenced nearly 6 decades ago. And I acknowledge that the questions we wish to answer will be different, but if the Brugela Catchment study can assist you with your question, I invite you to join with us online via the Brugela Catchment Study data portal. Here you can access additional information about the study, you can access the study publications, but the techiest part for me is you can view real-time data from the catchments. In this particular snapshot, October 2020, when the cropping catchment last had runoff, please visit us soon and have a look. Thank you.
Time for one question? No submission? What does the kangaroo control have any effect on the on the results?
So the question was, does kangaroo control or macropod grazing pressure have any impact on the results? Very early on in the land development of the Briglow belt, it became apparent that the moment you clear Briglow and plant an improved pasture or a nice wheat crop, you attract every macropod in the district to go and eat it for you. So our study site is in fact macropod exclosure fenced, so we're looking at the agricultural implications only removal in grain and beef. We don't actually have a native grazing pressure on it. So it just took one extra confounding effect out.
Thank you.
Thank you.
Next up we have Colin Schiller from Erlanger Community Erosion Control Group. Okay. Yep, we're running out of time there.
Right to go, is it right? Good morning. I'm helping Rob Savoury out on this project. He's done most of the work out there. I gave him a bit of technical backup from an erosion and sediment control perspective, but it's a situation started from the old seismic lines at Erlanger, and the landholders out there having a lot of difficulty retaining the soil and preventing erosion. Sorry, I'll just work this out. Which button we got?
Just that one there.
Agreement?
No, that's the laser.
Up.
That goes backwards. That one goes forward.
Okay. So on Belbombury Station, this is the type of erosion that it's gradually progressing towards. There's probably about 3,000 or 4,000 hectares at the moment covered in between these properties. The Molnar, that's the gully head itself, a very small amount of topsoil there, quite unstable. But once it punches through, and unfortunately the seismic lines may have initiated that initial form. Animals certainly initiated as well. That's further down on the Molnar Station job where it's down to a bit over 1 metre deep now. So there's quite a bit of soil moving in that country. The third property that got involved in the trial work was at Cranston. So they're roughly between 100 mil and 250, 300 mil deep in the erosion that's occurred on their property. So they're losing a lot of good productive soil very quickly from a combination of the soil chemistry and the grazing and, well, I suppose lack of rainfall in the last few years as well, followed by a small amount of rainfall that then just tears it away. So the group that got together, Rob coordinated and gradually came up with a few different strategies to try to stabilise the country out there. These are where the properties are, Erlanger, where the new dinosaur museum is, and there is actually some trials outside the museum as well to try to stabilise their drainage channel because it's opening up. The rainfall, roughly 286, 300 mil, not a lot to work with, but when it does fall, it's actually quite devastating on the soils. So there's the soil test from Molnar showing the 0 to 200, then 200 to 600. pHs are reasonable, 6.2, 7.3. There's particle size is reasonable. Acidicity kicks up a little bit once you get under that 200. We haven't found much over the 20% as yet, but the ESP We certainly keep an eye on, as well as the magnesium levels in there, and the particle size. So that's a fairly typical soil test. Where the issue tends to come in is just from the actual slaking side. It opens up really quick with 15 to 20 seconds. It's just flattening out. So that photo there is 20 seconds. It's just gone. So it's hard to stabilise. The camera, it's very low nutrient, very low capacity. So trying to come up with a simple system that could be a little bit practical out there with the landholders. You can't really put a lot of ameliorants on. It's hard to get organic matter. It degrades very, very fast. So we needed to divert what runoff water we could. The area was surveyed so we could level it. It's roughly less than 1 in 1,000 now, but it still needed a little bit more levelling in some areas. Then we used a dissipator concept similar to what we used in erosion and sediment control to reduce some of the velocity. We added a polymer. There's quite a few soil binder polymers coming out into the construction side of the industry, and that's where I normally work, in erosion and sediment control. So we had a choice of probably a dozen different polymers that we applied, similar to mine sites and railway lines. We narrowed those down to something that was a bit more practical for a landholder to put out in a small area. And then started spacing rocks similar to an energy dissipator and cemented them in place with a binder. So in the really simple form, we had a diversion bank bringing a flow into a control area, levelled, graded, levelled, little bit of compaction. That's just the band of polymer going down in the first stage work. Fairly heavy, but roughly about a 20% concentration. That's now moving back to 5 and 10% concentrations and making it a bit more applicable to a water truck or a tractor. Once the soil is sealed, the rock goes in, generally to 100 mil to 200 mil particle size rock with 100 to 200 mil spacing between them, because we're just trying to reduce velocity. We're not trying to trap any organic matter, because if we trap it, we end up with a contour bank and diverting the water where we don't want it to go. But that's pretty well what it looks like just after it's partially done. That's fully stabilised. Just to control the flow and water going through it. There's a typical rain event out there of roughly 12 mils. I'm just trying to hold it, slow it. There's not a lot of colour in that runoff water, so it's not from the acidity side. And that's after the rain event. We've probably had 5 to 10 mils of actual soil loss coming through there. So something simple like that system has been able to save quite a bit, and there's now extending out from those areas to larger systems, and there's one plan almost a kilometre long just to try to break it and slow it and divert it. So very little soil movement. These gaps is between about 10 and 15 mil, and we have the discharge downstream of the little spreader. We have been trying a few different grasses as well in there. They were successful originally, but then they were all taken out by locusts. So once you've got something green there, a bit like the macropods in the Briglow, as soon as you give them something on the buffet, they're straight in, and so it's gone. And this is a really short presentation because Rob's the main man. I must apologise. So I'd like to say thank you to the Eromangbo contracting that helped out. Simon Buchanan pitched in from Landlock and gave us a bit of extra help. The Vital Chemicals provided the binders, and the 3 landholders there, Alan Murray, Scott Pegler and Ralph Walker, all jumped in and are pitching in. So this is just going to be expanded out from now. So ladies and gentlemen, that's it. Short and sharp.
Any questions?
Yeah. Fairly important if you're trying to get vegetation going. Not as important for the rock. They do kick it around a bit, but the binder is held fairly well. They're running a beast on about 30 acres out there. So it's there is stock in there, but the binder's held the rock together. I think at 5% binder it may not. They'll probably dislodge those, and we may have to make the dissipators 1.5 metres, 2 metres wide.
Could you exclude stock as well? Have you
We'd like to, but the paddocks are pretty big. And if you go and lock out 5,000 or 6,000 acres, you have an economic impact on the landholder. So in some of the more degraded areas, they're going to get fenced off.
Is that how big these areas are?
There's some very large areas, yeah. Yes, very large.
If you made it 1.5 metres wide, would the stock go over it?
They walk through them and tend to trip, and when they trip and kick, that's where you lose your rocks. But you can't really put your rocks too deep, and we don't want to go too high a rock. So it looks like the 100 to 200 mil sizing is about efficient enough, but they certainly dislodge if you've got a 1 tonne animal going through.
Yeah. So the spacing between them...
Keeping a 100 to 150 mil gap. If we go too tight, you get a bit of debris that'll wash down, block it, then all of a sudden you've got a contour bank and you're moving it the wrong direction. We might be able to go a bit wider, but we're just not sure. At the moment, we're looking to extend it, take them out to half a K to a K long, and just break that flow a bit more. So, yeah. It's an unfunded project, so these guys are just getting together and doing what they can with very, very limited resources. So, yeah. Yeah. No. I didn't yesterday, unfortunately. Well, I'm actually up here on holiday when Rob said, can you pitch in and help? So I only got to one day of the Soils Conference. And yes. Whether using water to back up the water. Yes. Yeah. Very similar. It sounds like a presentation given in Darwin beginning of May at the Ecological Restoration Conference, and they had some big ponding trials there in either South Australia or New South Wales. We might be able to pond it, but we're just worried about any areas where you might have a tunnel initiated. We don't want to hold it too much, because if it does punch through that surface, that's really only 30 to 50 mil deep, it's going to open. Yes, yes. We have tried some of the ironstone gibber, and it seems to be a 20 to 30 mil size at a reasonable coverage with no gaps more than about an inch and a half, so 30 mil. We're getting stability as well, but that's once our slope starts coming up around 1%. The small gibber seems to work, yeah. I had good success using the ironstone gibber down at Miles on some of the coal seam gas batters. But if you get that particle size wrong and go too big with too much, it just goes through and tears it. Yeah, you really need, but in Miles you can put gypsum on it. Out here we can't really do gypsum or lime, it's too far to take it. We can bring it up from Swan Hill or Menindee Lakes, some of those areas, but the freight's the killer, Terramanga. It's not easy to get anything there. Yeah. In some of those already scalded areas, vegetation or debris is actually giving a better job, and the more we can spread the timber over, then it'll lock the soil together a bit too. And that's why we tried the vegetation. But as soon as we got a decent leaf on it, the grasshoppers just took it out. So.
Could you use these to put above, like where you've got a gully erosion, you recontour the gully erosion and put it above it to try and slow the water?
Quite possibly, yes. So yeah, the gully erosion, where the nick point is, or that initiation of the gully, if you can spread out that water flow coming into it and disperse it, yes, there's a very good chance, yes, that it will go. It'll depend on that flow of water, because we're only talking 100 to 200 mil rock. The specific gravity of the rock's about 2.1, so it's not a real heavy rock, and feasibly you'd want to increase your weight of rock to if you've got gully erosion, because you have a higher flow rate. We've only got very slow flow rates out there. The stone wall on that one is roughly about 12 months. It's a PVC PVA product. It's a step up from the old polyacrylamides that used to be used, and it was actually sorted out after the Christchurch earthquakes and the liquefaction and the asbestos dust. So the technology in soil binders has increased out of sight in the last 8-9 years. So it breaks down to pretty well nothing, and there's no contaminant there, so we use it a lot. If you're driving on the coastal highway projects, you see a green batter. Generally that is a soil binder now, whereas if it's at the end of the project, that'll be a hydromulch, where they put mulch in with the tackifiers or glues and spray it out. So the soil binders we're using everywhere, very short-term concentrations. On the Adani railway line, I've probably used a bit over 140,000 litres of binder just to hold the soil in place for dust suppression. Short term, that's only 6 weeks it lasts. So up on there, but yeah.
All right, thank you. Okay. I'd like to invite up Samandi Gurathanda from the University of Queensland.
Okay. Hello, everyone. Yes. Thank you for being here today. I'm Samadhi, and I'm going to present you part of my PhD project, assessing the influence of biological soil amendments on accelerated conversion of coarse soils to functional soils. First, let me explain to you the problem. Open-cut mining is one of the prime reasons for environmental degradation that we observe in Australia today. From pre-mining preparations of topsoil removal or burden removal to until the mine ceasing, the degradation of ecological conditions is so drastic, and once the mining stops, the right decision would be to restore the ecosystem to pre-mining conditions. However, it is given the severity of the degradation, the rehabilitation is the best option that they can opt for, that is rehabilitating the mine site into pasture land or agricultural land. Even this rehabilitation is harder because of the limited availability of functional topsoil that is caused by two reasons. One is the swell effect. That is, the post-mine area, land area that needs rehabilitation is larger than the pre-mine land area because of the spoil piles, and the available topsoil is not enough. And the second reason is the loss of topsoil functionality during long-term storage. With stockpile age and stockpile height, it reduces the microbial functions related to nutrient cycling, and so it reduces the plant available nutrients. Under such topsoil deficit conditions, the next available option is to use the mine overburden. By origin, the microbial biomass in mine overburden is lower, and also microbial functions related to nutrient cycling, low organic matter, as well as harsher conditions such as salinity, sodicity, acidity, alkalinity, those conditions. So if you're using overburden for rehabilitation purposes, we need interventions. Soil is a living matrix, and microorganisms govern the soil health. So the approach we choose was to incorporate conventional, commercially available biological amendments as biostimulants to restore the microbial functions related to nutrient cycling, with the assumption that it will improve coarse soil into functional soils. With that, we went for a field trial in Bourne Basin by profiling a spoil pile in July 2018, and at that time we took soil samples and checked for soil chemistry, where we found that it is highly sodic and low in organic matter. To compensate for that, we incorporated gypsum and mulch, and in September 2019 we incorporated biological amendments, compost, worm juice, and manure. In November the same year, we included a seed mix that consists of corn, sorghum, and millet. In December, we took the first samplings. In Bourne Basin, the rainy season starts in December and goes through until February, and after that, the whole year is pretty dry. After December sampling, we collected 3 more samples and completing 1-year field trial. From the second sampling, we collected a reference soil from adjacent unmined area so that we can compare the amendments and the spoil control to natural soils. After collecting these soil samples, we tested them for soil chemistry, soil structure, and soil microbial functions. So microbial functions were assessed using enzyme activities, microbial enzyme activities, important in major biogeochemical cycles. Then we use this chemistry data and enzyme activity data to find out whether there are any deficiencies or improvements in biogeochemical cycling in amended soil compared to control soil and reference soil. So in carbon cycling, we used beta-glucosidase activity as the enzyme and the organic carbon, and there we found out that regardless of adding mulch, the amended areas as well as the spore control has significantly lower organic carbon compared to the reference soil, and beta-glucosidase activity was significantly higher in composted area compared to spoil area only in December, but couldn't find the same trend afterwards. However, beta-glucosidase activity was 50% of the time significantly lower in amendments compared to the reference soil. These data suggest that there's still a carbon cycling deficiency in amended soil. Nitrogen cycling was decided using the urease activity. So like in the carbon cycling, urease activity was significantly higher in composted area compared to the spoil area in December. And the interesting fact was that with the time, spoil improved its enzyme activity, and by the end of the field trial, it was significantly higher in spoil compared to compost. The nitrate ion concentrations follows a similar trend. In the beginning, it was significantly higher in composted area compared to the spoil, couldn't find the same trend afterwards. Total nitrogen in general was significantly lower most of the time in amended areas compared to the reference area. So this suggests, again, a nitrogen deficiency, cycling deficiency in the spoil areas. Phosphorus cycling was decided using alkaline phosphatase activity and acid phosphatase and available plant phosphorus. So available plant phosphorus follows the same trend. It was significantly higher in December in composted area compared to the spoil control. Didn't follow the same trend afterwards. Alkaline phosphatase activity was significantly higher in composted air in all the amendments in December as well as in February, but the interesting fact again was that spoil improved with time in phosphatase activities. The structure was determined using Emerson's aggregate stability test. These images were from the last sampling. So as you can see, all the amended areas and spoil control has slaking and dispersion compared to reference soil. It is consistent with the chemistry data that we found out that all the amended areas and spoil control has significantly higher exchangeable sodium, electrical conductivity, sodium ion concentration compared to the reference areas. So regardless of the gypsum application, all areas, gypsum application, it shows that the EPS was, exchangeable sodium percentage was not reduced and the structural stability was not improved. So these are the images after the 1-year field trial. As you can see, none of these amended areas or the spoil control has established a sustainable plant cover. And also in the spoil area, we can see erosion. And interestingly also, the mulch that was added 1.5 years ago was still, we could see without degradation. So from this study, we came into 3 major conclusions. Firstly, compost accelerate spoil microbial activities for a shorter period of time, but fails in long-term recovery. This is because the microbes that are important for geochemical cycling in these biological amendments were unable to establish under harsh edaphic conditions of the soil. Secondly, the natural recovery of most of microbial functional activities in coarse soil is possible after 2 years. As you can see in the biological activities, it shows an upward trend in enzyme activities. Thirdly, gypsum incorporation does not reduce soil solidity and dispersivity under irrigation or rainfall restricted conditions. As you know, the Bound Basin has a limited rainfall, and also because of the ongoing drought, it was harder for them to irrigate. So the displaced sodium from the gypsum was not leached out, so it failed in improving the soil structure stability. With this conclusion, we move to future directions. So we suggest coarse soil rehabilitation needs a site-specific approach. Soil, soil physics, soil chemistry, soil biology, and plants interacts and interconnects with each other to maintain a sustainable environment. So degradation in one property creates a ripple effect and fails the whole system in the long run. So we suggest, rather than focusing only on establishing a plant cover over the spoil, we suggest the rehabilitation strategies should focus on identifying the underlying issues in these properties and treat them, implement interventions to treat them and improve the soil as one system to support sustainable vegetation. That is exactly kind of what we did. We created a custom-made microbial biofertilizer that includes bacteria, fungi, and cyanobacteria. These microbes were isolated from the reference area, and these are function-targeted microbes. We grew them in media that has a chemistry similar to the spoil chemistry, so they are already adapted to these edaphic conditions. And then we incorporated them in a pot trial with the same spoil, with the assumption that since they are adapted to the edaphic conditions of the harsh edaphic conditions of the spoil, they can establish in the spoil and still improve the biogeochemical cycles and improve the plant available nutrients and structure to support a self-sustaining vegetation. From there onwards, we are continuing this pot trial for 6 months, and then we go for a field trial, that is a 1 hectare field trial. We're going to try this biofertilizer in the field trial to see how this microbial consortium can accelerate the conversion of spoil into functional soils under natural conditions. Finally, I want to thank my group in the lab, Vale Geomicrobiology Lab in University of Queensland, and thank you for being here today. Questions? Yep.
In your experiment, you've seen there's a decrease in microbial activity. Is that attributed to a loss of easily respirable organic carbon? Or is it a loss of certain populations of microbes?
I would suggest that these conventional, commercially available biological amendments are like general microorganisms that you would use in agriculture, but these are like specific soils with harsh environmental conditions. I would suggest that they failed in establishing themselves in the soil. That's how the activity is reduced.
There are some interesting commercial microbes coming out of underwood now. Yeah. I've just used them on spoil on a coal mine up to about 70 hectares, but I noticed you have the heavy wood fibre mulch there.
Sorry?
Heavy
mulch?
Yeah.
Mulch. Oh, okay.
Yeah, but the long-term wood fibre mulch, have you done any trials with shorter-term mulch like soil or stubble or
This is actually grass clippings and also some bark. So we decided the amount of mulch according to the best practice guidelines in Gulf Basin for mine management. They wanted, they say like the rehabilitations would fail if the open carbon doesn't increase up to 1%, and the beginning was 0.67. So that's why we incorporated that. Maybe as you suggested, if we go for like stubble. Yes?
It's also actually because you've got this exclusive story, you get runoff.
Yeah.
So the soil moisture is reduced.
Yeah.
So you're in a catch-22 situation. Like it's not correct.
It could be a reason like the moisture deficiency, but problem is like mining industry doesn't want to irrigate, and again this basin is under drought condition, so they want a hardy solution that like the microbes or whatever we are adding that can survive in these conditions. That's what actually we made it